I hope you can see the screen. I modified the title a bit because to me, now that I'm dealing with the topic radon for some 20 years already, to me, it is possibly the most underestimated geohazard in urban areas. This is easy to explain, at least in my thoughts. So what are the facts? It's a naturally occurring radioactive gas that is considered an indoor air pollutant. That's a fact. It's a fact that short-lived radon decay products can damage the cells in the lungs, and they're the genetic material. This may cause lung cancer. That's also a fact. And the statistics we know about in Germany is that some 5% of all deaths from lung cancer can be attributed to radon. That's in total some 1,900 deaths per year. And I don't know which other geohazard, let's call it geohazard, is causing that many deaths per year in a country. And the health risk posed by radon is actually higher than the risk posed by asbestos. Everybody knows about asbestos. Some weeks ago, I had to repair the roof in the neighbor's building I was helping, and it was kind of asbestos around. And you can imagine, as you know, and everybody knows, the reaction, what to do and what to take care about, and so on and so on. So that's what people are aware of. But radon, almost no one is talking about it. At least in Germany. I know it's different in other countries, Scandinavia, that's different. But as geologists, we know that radon occurs in almost every rock, every soil. And in the end, the measurable radon concentration can increase significantly in the vicinity of tectonic faults. That's something given. And that's why the European Union was looking for some action. In 2014, the European Council directive has been established, where it's about the basic safety standards for protection against exposure to ionizing radiation. In 2017, then, in Germany, the according law has been established, the Radiation Protection Act, and there a radon action plan was requested by the federal states. And that's why Hesse is given here, because I'm working for the Geological Survey of this federal state. So for our federal state, we need to designate radon precautionary areas. That's what the task is. The question now is, why is this a task, and what is a radon precautionary area? This is some sketch that is intending to describe the dependencies, the health risk coming from radon, or the geohazard related to radon. As geologists, we know about the subsurface. We know that there's a lot of rock around and soils around, different rocks, different soils, but they all have in common that they contain uranium. Some rocks more, some rocks less. Uranium is the mother nuclide, which turns into radium, which turns into radon. And now if we have some migration towards the surface, this radon can get in touch with the building, and if you have, say, cracks in your base plate, or if you have maybe no base plate at all, that's quite common, happens quite often. Or if some pipe openings are not tight enough, then radon can get into the building, and the concentration can increase up to, yes, significant amounts. I will show you some examples later on, but that's described here. So we do have an interaction between the building, the construction, and the surroundings, the soil, the subsoil, the construction ground, the rocks, and that's what the problem is about. So the radon precautionary areas, they have been they have been assessed or developed using a so-called Radon Potential Map. And this is something which has been modeled by the Federal Office for Radiation Protection in Germany. And they used for this map soil air measurements, permeabilities, and indoor measurements. And what you can see on the map is 3 colors. Every color is representing a category. The bright bluish color is showing a potential of less than 22. And then we have the middle one, which is 22 to 44. And the dark bluish colors, they represent potentials higher than 44. I don't know, but I think that something comparable should have been done, or should be available for most of the other European countries. So what does it mean in the end? You can see the federal state, you can see the counties, and you can see the distribution of these tiles, 10 by 10 kilometers each tile. And only those counties have been made, or would have been made, a radon precautionary area where the percentage of those tiles with a potential higher than 44 is exceeding 75% of the total area of such a county. And this is not given in any of the counties. So even if there are some tiles where we do have a high radon potential, where we do have the risk that the average radon concentration in the room air is exceeding 300 becquerel per cubic meter per year in the average, even if we have such areas given, the overall area, which is the county, has not been made a precautionary area. Yes, but in the end, this is just statistics. It's a good model. It's useful. It's helping a lot to make people more sensitive and to focus our works in given areas where we need to get more understanding. But it's statistics. So if we're talking about the statistics, we can switch to maybe the reality, and the reality is much more difficult. The measurable radon concentration depends on many parameters. Something we already have seen is the building conditions, the foundation type. Is there heat insulation? Yes or no? What about the building material? Then, of course, the meteorological conditions are influencing what we can measure. The temperature has an impact, like the air pressure. And of course, the subsoil. So the measurement environment is impacting a lot what we can measure. It's the geochemical composition of rocks and soils. It's the permeability, it's the tectonic inventory, and soil physics. While the building conditions are easy to assess and the meteorological conditions are easy to measure, we do have the subsoil, the underground, as the most difficult part in this context. And at the same time, it's the most important one, I would say, from a geological point of view. Of course, others say, who cares about the geology and the rocks and all the uranium and radon that is given there, as long as we have all the capabilities to build proper buildings. Then we don't need to care about this at all. But the reality is showing us something different. The development of radon is given here. That's the decay chain, and down there you see it's at the radon 222 with a half-life of 3.8 days. And it's not the radon itself, it's the decay products which are causing the problems, because their decay happens after 3 minutes, which is polonium, after 26.8 minutes, which is lead, And then we have bismuth with 19.9 minutes. And if you're inhalating those heavy metals, and if the decay takes place in your lung, then we get the damages we are talking about. So it's not the radon itself, it's more the decay products which are causing the problems. But radon is the element we need to measure, or is maybe the only one that is useful to be measured because of its relatively long life of 3.8 days. The others are difficult to measure. That's why we focus on radon. So we know about more than 200 uranium minerals, and most of them are not relevant, but some are, like monazite, zircon, titanite, and apatite. There, some uranium is substituting other components of the minerals, and in a thin section, it probably looks like this. We have some zircon there and some bismuth there, and it's almost not to see. That's why I was stating something like the scale. It's just 0.01 centimeter, which is very tiny. It's the same with another thin section where you can see the zircon there. And if we know about these minerals, and if we know about their occurrence in the rocks, then we can do some statistics and see that the crystalline basement in our federal state, coming from the Geochemical Database, is hosting a lot of uranium, a lot of thorium, like the rocks in the Lehné Shield. It's a bit less. It's quite okay in the sandstone, but and in the tertiary sediments. But the Rotliegend and the tertiary volcanics, they also host some thorium and uranium. So I was talking about the Geochemical Database. This is how it looks like if you bring it on a map. Every point is representing a sample, and every sample has been analyzed for uranium, thorium, and others. And most of the samples do not show any problems in terms of their concentration of uranium and thorium. The average concentration of uranium in the Earth's crust is 2 to 4 ppm, and that's given in yellow. If the concentration is less, it's green, and if it's above the average, it's red. So you see on the left, the uranium is maybe a topic in the southern part of the federal state, in the Odenwald Mountains, where we do have the crystalline rocks, and here and there in parts of eastern Hesse also some samples show higher concentrations of uranium. It's comparable with thorium. So the average in the Earth's crust is 7 to 13 ppm, sorry. Again, yellow, green is less, and red is higher. And still we are focusing on the Odenwald Mountains down there and parts of the Vogelsberg volcanics complex. Yeah. But if we now get into the details, because we are talking about the urban areas and not just the geology for all the federal state, then I would like to draw your attention down to this area of Darmstadt. Here again, the distribution of the elements of uranium. We do have Permian sandstones with uranium content mostly below 2 ppm, here and there between 2 and 4. Then we do have diorite, quartz diorite, and gabbro. Again, the uranium content mostly is less than 2 ppm, here and there 2 to 4. But the granite, gneiss, granodiorite, there we often have more than 4 ppm. And in addition, there's some input from heavy minerals delivered by the rivers, and by lateral dislocation. Weathering processes are taking place there, dislocating the material into the valley, the Upper Rhine Valley. So if we get back to this radon potential map, for this area, we see, and this is two information maps. The left is showing the modeled soil air concentration, the concentration of radon in soil air. Of course, that's based on real given measurements, but the size of every tile is 3 by 3 kilometers, and we have at the moment for the entire country, Germany, around about 6,000 measurements only available. So it's easy to understand that not every tile is described by a real given measurement. That's why it is modeled. And for this area of Darmstadt, you can see the boundary of the city. We have some soil air predictions that range between less than 20 kilobecquerel per cubic meter and more than 40. That's what is given in the model. The radon potential for the city is described by the numbers on the left map. Remember, higher than 44 means difficult. Having numbers like 3.6, 60.3, 1.3, people might think this is not a problem at all. Not a problem at all. Okay, yes, but it's to cause for the local decision makers, because, and that's a slide I was presenting, I don't know, I guess 2 years ago already. This is a measurement. This is an indoor measurement in a building in Darmstadt, which is the Congress site. And we have concentrations of up to 21,000 becquerel per cubic meter room air. That's a lot. And we have measured the soil. And there we found some 340,000 becquerel per cubic meter room air. So the prediction in the model is ranging between 20 and maybe a bit more than 40. In fact, we have 340, 20 and 40,000. In fact, we have 340,000 at this site. The room air is supposed to be not a problem at all, but we have 21,000. And of course, this sticks to the geology, and this sticks to the rocks. And in this particular case, this sticks to a tectonic fault, which is active and which is acting as migration path for the soil gas and thus for radon. That's one example. Another one, that's the capital of the federal state, Wiesbaden. And I just want to give some few examples to show that this problem is given almost everywhere. This is Wiesbaden, the capital. Again, the geology. We have some Devonian rocks. We have some tertiary deposits, some quaternary deposits, and the concentration of uranium seems to be not critical. Almost every sample shows less than 2 ppm. Sounds good, but another measurement here in a private building in the basement, a maximum concentration of 2,230 becquerel per cubic meter room air. The average is 846. 846, that's almost 3 times higher than the reference level like it has been defined by the European Union. Of course, people measuring those concentrations in their basement are concerned. They are afraid that there's something going on which is impacting their health. And that's why they need help, and that's why they want support, and that's why they want to find a solution, how to get rid of this radon. That happened in Wiesbaden. It's the same in another area, Bad Nauheim. We have this area located to the west of the Vogelsberg volcanic complex, where we do have tertiary basalts and trachytes. As you can see, the variety of concentrations of uranium is given. We have most of the samples without any indication of higher concentrations. A few have a higher concentration, but if we get into the city itself, and that's what you can see, it's the tectonic faults, and then the red lines, and then we have the points which are indicating measurements, and the measurements show concentrations of up to 1.5 million becquerel per cubic meter soil air. This is the number 19.79, so it's the multiple of the minimum, and this is a lot. 1.5 million. Yes, and of course we know as geologists, and that's why we made these profiles, that the radon is coming up along the tectonic faults. So the geological map is not giving a tectonic fault in this area. It's in the north, but there's no extension to the south. Having the measurements given the way they are, I would interpret that the tectonic fault has to be extended, and then it would have a course which is, of course, in the end, getting in touch with buildings like the one down there, which is a hotel, and there are schools around. So, and there's another installation around, which is the so-called Sprudelhof. That's a spa area. And again, we see the faults on the left, trending from northwest to southeast, and another one which is trending from southwest to northeast, and the blue points, they indicate not soil measurements but indoor measurements in the basement, and the concentrations, they vary between 95 and 2000. And this is telling us something about the reason why concentrations can be higher or lower. Of course, we have to pay attention to the fault. So there's more radon coming up along this fault. So it's available for migrating even into the building. But if the building is in good conditions, like it is down there in the southeastern part of the complex, where we do have the 95 becquerel, this has been renovated already, this area. And up there, in the northwestern part of the complex, the works are ongoing. Back in the days, in 2019, when the measurements have been made, they didn't start to modernize the building. So there's an interaction. Like the final example up there, the area of Kassel. Again, we have volcanics, we have tertiary deposits, we have tectonics, like this so-called Kassel graben structure trending from west to east. There's basalt, Triassic sandstones, Carboniferous and Devonian slates, uranium contents here and there, a bit higher, but yes, mostly uncritical. And that's another measurement from a basement in a private building. Again, we do have a maximum of more than 2000, and the average is 1200. And those people, they need help. And this is 4 examples. I don't know how many buildings I have measured in total with time series measurements like the one that is presented here. I think it's not that many. It's round about 10 so far, and more than half of the buildings had increased radon concentrations. Only a few did not show any problem. So it's more than 50%. Whenever you start measuring, more than 50% so far where problems pop up, radon-related problems. So what did I learn? What did we learn? Radon appears everywhere. And in given concentrations, it is a geohazard, and especially and only in urban areas, because only where people are living, radon is impacting health of people. So maybe that's the only hazard which sticks so close to people. And the measurable radon concentration, that varies locally a lot. You can measure some 10,000 becquerel in the soil air here, and 2 meters to the right, it's 50 or it's 100,000. happens. That's normal. Statistical or global approaches in estimating and assessing a radon potential or health risks arising from radon are not leading if you need to address a local situation, if you need to understand what's going on there locally. And then in the end, the more heterogeneous the deposits are and the more complex the tectonic setting is, the more geological expertise is needed to address the overall topic sufficiently. And yes, that's what I wanted to share with you.